All right, so here we're going to be proving some of our theorems that deal with perpendicular lines that we're eventually going to use as reasons in our proofs. So before we get into that, we have to define a couple of things. A perpendicular line, a line is perpendicular to another line if and only if the intersection forms a right angle. So basically that if and only if part of that definition is saying that that's a two-way street. The converse and the conditional statement are both true. If we have a right angle, then we know we have perpendicular lines, and if we have perpendicular lines, we know we also have a right angle. When we do have a right angle, we can split that into two separate angles, and those are called complementary angles. And again, this is a definition. That's why we have this if and only if phrase in that sentence. If we have complementary angles, an angle is complementary to another one if those two angles have a sum of 90 degrees. Basically, they form a right angle. And all right angles are congruent. That is a postulate that we just know to be true. That seems self-explanatory, but it does need to be said at points that every right angle is congruent to every other right angle. So the first theorem that we're going to prove is the linear pair perpendicular theorem. And that states that if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So there's really two parts to that given statement, both that angle 1 and angle 2 are congruent, and that they form a linear pair that's shown here. So angle 1 and angle 2 are the same, and they line up along line H there. And we want to prove that line G is perpendicular to line H. So basically, we want to eventually get to these forming right angles, because if we have a right angle, we know we have perpendicular lines. So I'm going to start with my given statement saying that angle 1 is congruent to angle 2. And then from there, I want to think about how I'm going to show that these are 90 degrees. So I want to first show that these are going to add up to 180 degrees. So I'm going to say that angle 1 and angle 2 are supplementary. And that's by the definition of a linear pair. From there, I can actually say, now that I know that they're supplementary, I could say that angle 1 plus angle 2 adds up to 180 degrees. That's by the definition of supplementary. And now I can use substitution to show that both of these are actually the exact same angle. I know that angle 1 is congruent to angle 2, so I can actually substitute in two different ways. I'm going to say that angle 1 plus another angle 1 adds up to 180. I'm substituting in that angle 1 for that angle 2. So that is substitution. And there might be a more formal property name for this, but I'm just going to call this next step simplifying. I know that I have two of those, so I'm going to say 2 times the angle 1 equals 180. From there, I have one more step to prove that those are actually just 90-degree angles. I'm going to divide on both sides by 2. That's the division property of equality. That shows that angle 1 is equal to 90 degrees. And that's really what I wanted to prove. I know that these are both 90 degrees. So I know that G is perpendicular to H by the definition of perpendicular lines. So the next theorem we want to prove is the perpendicular transversal theorem. So in a plane, a transversal is perpendicular to one of two parallel lines. Then it will also be perpendicular to the other parallel line. So we have two things that are given here. H and K are parallel to each other, and we know that J is parallel to H. We want to prove that J will also be parallel to line K. So I'm going to start out with actually that second given statement J is perpendicular to H, which means that I have an angle here that forms 90 degrees. I'm going to call this angle 1. So I know that angle 1 is equal to 90 degrees by the definition of perpendicular lines. Now I'm going to jump into my other given statement. I'm going to say that I know that these lines are parallel to each other. So then I'm going to start associating angles on this intersection with angles on this intersection. You could do this in a bunch of different ways. Sorry, that is a given statement. So I'm just going to use corresponding angles because that's just the easiest one to see for me. I'm going to call this one angle 2. And I'm going to say that angle 1 is congruent to angle 2 by our corresponding angles postulate. I know I have congruent corresponding angles because I know that H and K are parallel. And now I can use substitution, or kind of the transitive property using, basically I'm going to substitute in 2 for angle 1 in that equation and say that angle 2 is equal to 90 degrees. And actually that's all I really need. Once I know that I have a 90-degree angle here, I already labeled it there, which I really shouldn't have done, but that corresponding angles postulate basically told me that those are the same angle. This, being a right angle, proves that J is perpendicular to K as well. And that's by the definition of perpendicular lines. Once I prove that I have a 90-degree angle, I've basically proved that I have a perpendicular intersection. Our next theorem is lines perpendicular to a transversal. So in a plane, if two lines are perpendicular to the same line, then they are parallel to each other. And this is basically just the converse of our corresponding, at least in this picture, that's the converse of our corresponding angles postulate. If I know that these two are the same, I have congruent corresponding angles, then I know that these lines will also be parallel. So I'm going to start out, actually it doesn't really matter which one I start out with because they're essentially the same. But I'm going to start out with that first one. M is perpendicular to P. And again, I'm going to have to label some of these angles. I'm going to call this angle 1 and this angle 2. So I know that angle 1 is equal to 90 degrees because I know that this is perpendicular. So that's by the definition of perpendicular lines. Then I'm going to make the exact same claim about that intersection. I'm going to say that N is perpendicular to P because it's given to me, and that angle 2 is equal to 90 degrees because of the definition of perpendicular lines again. And now from there, I can conclude that these are actually equal to each other. I'm going to use the substitution property. To say that angle 1 is congruent to angle 2. And if I know that these angles are congruent, that and that are congruent corresponding angles, then I can use the converse of the corresponding angles postulate to say that these are actually parallel lines, that M is parallel to N. Our last theorem that we want to prove is the congruent complement theorem. So this is saying that if we have two angles that are complements to the same angle, then those two angles are congruent. So 1 and 2 are complementary, 2 and 3 are complementary. So that's saying that 1 and 3 actually have to have the same measure. 1 is congruent to angle 3. So I'm going to just start off, again, this is kind of interchangeable, but I'm going to use angle 1 and 2 being complementary as my first given statement. And if I know that they're complementary, then I know that angle 1 plus angle 2 add up to 90 degrees. That's just by the definition of complementary angles. And then I'm going to make the exact same two statements about this set of angles. Angles 3 and 2 are also complementary. That's given to me. And angles 3 and 2 have a sum of 90 degrees by the definition of complementary angles. And from there, I can use the substitution property. I know that this is equal to 90. So instead of this 90 degrees, I can write angle 3 plus angle 2. So I'm substituting that expression in place of this 90 degrees. So now I know that angle 1 plus angle 2 equals angle 3 plus angle 2. That's the substitution property. And from there, I use the subtraction property of equality. I'm subtracting angle 2 on both sides, subtraction property of equality, to show that angle 1 is equal to or congruent to angle 3. So these are our 4 new theorems that we're going to use when we're dealing with right angles and perpendicular lines.